Hello, welcome to this course on 3G, 4G wireless communications. Last lecture, before we start today's lecture, let me begin with a recap of last lecture. We said a multipath wireless channel can be represented as a sum of L multipath components. Each component is characterized by an attenuation factor A and a delay tau, that is the ith path has an attenuation AI and delay tau I. We said the gain associated with the ith path or the power associated with the ith path is magnitude AI square arriving at a delay tau I. I can also represent magnitude AI square with Gi, the gain of the ith path, or also the power associated with the ith path. So, it can be represented as a power Gi as arriving at a delay tau I. And then we also said now in a wireless channel we have L paths, the first path arriving at delay tau 0, second path delay tau 1, so on and so forth, with the last path arriving at delay tau L minus 1. The first path has a power G0, second path has a power G1, so on and so forth, the last path has a power GL minus 1. So, now my signal is arriving over an interval of time, unlike a wired communication channel where there is only one path. Because there is no scattering in a wireless channel, because of the scattering and the multipath propagation environment, I have multiple components arriving. These components are arriving over a certain delay or a certain time interval. This is also known as a time spread, and this interval is technically known as a delay spread of the signal, that spread of time over which the different signal copies are arriving. We said this delay spread can be characterized by the quantity sigma tau, and we gave different expressions to compute sigma tau. We said one of the most popular ways to compute the delay spread is what is known as the RMS or the root mean square delay spread. For that we need to compute the average delay, which is tau bar. Tau bar is nothing but summation Gi tau I divided by summation Gi. So, if I look at Gi over summation Gi, it is nothing but the fractional power. Look at this, Gi is the power in the ith path divided by summation of Gi, which is the total power. So, Gi over summation of Gi is the fractional power. This is the fractional power in the ith path. I am taking the fractional power, multiplying it by the delay. So, I am computing the weighted delay, which is the average delay tau bar, and then I can compute my delay spread as the fractional power times the deviation tau I minus tau bar square summation whole under square root. That gives me the average delay or the root mean square delay. We also did an example in which there are 4 paths arriving with the different powers. The first path is minus 20 dB, minus 10 dB, and then so on and so forth. We computed the average delay of this channel or the RMS delay spread, and we said the RMS delay spread value is 0.8573 microseconds. And then we also said this power profile that we looked at varies from channel to channel. So, if we have a large number of users in my 3G, 4G wireless cellular system, I can look at all the channels and compute the average power profile, which is obtained by taking the expected value of these power profiles, or taking all these power profiles of different users and computing their average. That is known as the average power profile, which is phi bar of tau. And now, given phi bar of tau, I can compute the average delay spread as follows. I compute f of tau, which is the fractional power received at the delay tau, which is phi bar of tau divided by integral phi bar of tau. This is the total power. The numerator is the power at delay tau. This gives me the fractional power at delay tau across all users or on an average, and I can use that to compute the delay spread as average delay as tau f of tau integral 0 to infinity, and the average RMS delay spread as f of tau, which is the fractional power times tau minus tau bar square, which is the deviation integrated from 0 to infinity whole under square root. This is similar to what we did in the RMS delay spread, except that that was a discrete channel. Now, we have a continuous power profile. So, we are using the integration. And we also started with an example where I said the average power profile is given as alpha e power minus tau over beta, where alpha is 2 and beta is 1 microsecond. We said this is a standard exponential power profile in which the power arriving at the receiver is decaying exponentially with delay, and we were about to compute the power, the RMS delay spread of this exponential power profile. So, let me start today's lecture with a computation of the RMS delay spread of this power profile. We said phi bar of tau equals 2 e power minus tau over beta, where beta equals 1 microsecond. The fractional power profile in this case f of tau is given as phi bar of tau divided by integral 0 to infinity phi bar of tau d tau. Let me first compute this quantity phi bar of tau d tau. Phi bar of tau d tau integral 0 to infinity, this is the total power. Remember, we said this is the total power, this is nothing but 2 e power minus tau over beta integral 0 to infinity, which is nothing but 2 beta integral e power minus tau over beta 0 to infinity. This is nothing but 2 beta. Hence, f of tau is phi bar of tau over integral phi bar tau d tau, which is nothing but phi bar of tau divided by 2 beta. Hence, this can be derived as the fractional power profile can be derived as 2 e power minus tau over beta divided by 2 beta equals 1 over beta e power minus tau over beta. All right. So, this is the fractional power profile. This is also the, let me write this down, this is the fractional power profile. This is the fraction of the power that is received as a function of the delay tau. All right. So, this is the fractional power profile. Now, the average delay tau bar is nothing but tau bar equals tau f of tau d tau. This is nothing but 0 to infinity tau over beta e power minus tau over beta d tau. So, I am computing the average delay, I am saying that is tau times this is the fractional power received. So, I am taking the delay, weighing it by the fractional power, integrating from 0 to infinity, that gives me the average delay, that is nothing but integral tau over beta e power minus tau over beta, and this can be shown to be beta. So, the average delay tau bar equals beta equals 1 microsecond. Remember, beta is a constant whose value is 1 microsecond. Now, let us compute the RMS delay spread. The RMS delay spread is nothing but sigma tau square is given as integral 0 to infinity tau minus tau bar square f of tau d tau. This is nothing but integral 0 to infinity tau minus beta square 1 over beta e power minus tau over beta d tau, and I will not compute this integral explicitly over here, but you can compute it and you can verify that the value of this integral is beta square. So, sigma tau square is beta square, sigma tau is square root of beta square, which is beta which is equal to 1 microsecond. Hence, what have we derived so far? What we have derived is for the exponential power profile given as alpha e power minus tau over beta, that is I have a power profile which is exponential, right. So, the exponential power profile with alpha equals 2, beta equals 1 microsecond, we have derived the sigma tau or RMS delay spread equals 1 microsecond. Alright. So, we have derived for an exponential power profile, that is when you average across all users in the cell, if the power profile, when the power profile looks like a decaying exponential, that is as a function of the delay, the arriving power at the receiver is decaying exponentially with the parameters alpha and beta, that is the power profile is alpha e power minus tau over beta. The RMS delay spread of this wireless communication channel is nothing but beta, which is 1 microsecond. That is, most of the power is restricted to an interval or a delay spread of 1 microsecond in length. All right. So, now with that intuition, let us go on to the next step, which is characterizing the delay spread of typical outdoor channels in 3G, 4G wireless systems. Let us come to the topic of average delay spread in outdoor channels. Let us consider a cell, a typical cell with a base station somewhere in the center and a mobile somewhere at the edge of the cell. We know that typical cell radius is around kilometers, is around 3 to 4 to 5 kilometers, sometimes 10 kilometers. All right, let us call it around 2 kilometers. All right, so the typical direct path is around 2 kilometers, and let us say a scattered path, let us say there are scatterers at the edge of the scale such as trees, buildings and so on and so forth, and there is a scatter path that is coming towards the mobile. So, we are saying that we are considering a scenario in which there is a cell phone at the boundary of the cell, there is a base station at the center of the cell, the direct path is the radius of the cell, which is around 2 to 3 kilometers, which is the order of kilometers. There is a scatter path which is also of the order of kilometers, which is let us say around 3 to 4 kilometers. So, the distance or the difference in the distance between the direct path and the scatter path. So, let me write it down clearly over here, the difference in distance between scatter path and direct path is approximately of the order of kilometers, right, because the direct path is around 2 kilometers, the scatter path is around 3 to 4 kilometers. So, the distance, the difference between these distances is around the order of kilometers, which means the delay. So, let us say the direct path is arriving at tau 0, direct path is arriving at tau 0 is approximately equal to 2 kilometers over c, tau delayed, which is let us say a tau 1, which is the delayed path, is arriving at approximately 3 kilometers over c. This is, so the delay spread, which is the difference between the arrival of the direct and scattered path, the delay spread or difference in time between direct and scatter path is approximately the difference in distance, which is 2 minus 3 kilometers. These distances are of the order of kilometers. So, the distances are also of the order of, the differences are also of the order of kilometers. Let me say it is approximately 1 kilometer divided by c, which is 1000 meters divided by 3 into 10 to the power of 8 meters per second, which is c, which is the velocity of light or velocity of an electromagnetic wave in free space, and this is hence equal to 3.33 microseconds. All right. So, what have we said so far? So far we have said, if you look at this, we said the differences in the distance between the direct path and the scatter path of the electromagnetic wave in the wireless cellular system or the transmitted radio wave is approximately of the order of kilometers. All right, which means the delay, the spread of time over which these signals are arriving is nothing but the difference in distance over the velocity, which is of the order of, the difference in distance is of the order of kilometers over the velocity, which is 3 into 10 power 8 meters per second. This is 3.33 microseconds. So, now I can say the outdoor delay spreads in 3G/4G wireless communication networks or wireless cellular networks or wireless communication systems are approximately of the order of microsecond. Remember, the calculation that we did earlier just in the previous page is not an exact calculation, it is an approximate calculation. We said the distances are of the order of kilometers, hence the delay spreads are of the order of microseconds, typically around 1 to 3 microseconds. So, the outdoor delay spreads are approximately around 1 to 3 microseconds. Let me take you to a standard values of delay spreads that are listed in literature. For instance, let me go through this example given in the slide over here, where different measurement campaigns have been carried out to measure the delay spread of the arriving multipath components in wireless communication systems. At frequency 910 megahertz, there have been delay spreads that have been reported that are around an average delay spread of 1300 nanoseconds. Nanosecond is 10 power minus 9 second, each nanosecond is 1000 microseconds, each microsecond is 1000 nanoseconds. So, this is approximately 1.3 microseconds. All right. Also, you see in a worst case situation in San Francisco, the delay spreads are around the worst case, that is the maximum delay spread is around 10 to 25 microseconds, and you can also see different values. For instance, in this case, average extreme case is around 1.9 to 2.1 microseconds. Hence, average outdoor delay spreads are around microseconds. So, let me go back to my lecture here and let me say write that point again, which is average. Remember, we are talking about outdoor, average outdoor, that is for outside cellular communication, average outdoor delay spreads are around 1 to 3 microseconds. All right. And indoor delay spreads are of course smaller, because inside the distances are smaller, the wall to wall distances, the wall to wall scattering distances are smaller, therefore, the indoor delay spreads are much smaller. Typically, they are of the order of 10 to 20 or 10 to 15 nanoseconds. So, indoor delay spreads For instance, if you are employing wireless LAN system inside a room, that is an 802.11b system inside a room, the indoor delay spreads, because the distances are smaller, the indoor delay spreads are around 10 to 50 nanoseconds. So, this is the typical value of the indoor delay spread. Now, let me go on to another important idea related to delay spread. We have looked so far at the delay spread. We have said the delay spread is nothing but that interval of time over which signal copies are arriving. This happens because of the different multipath components. The first component is arriving, second component, so on and so forth until the nth component. So, these different components are arriving over an interval of time, hence there is a delay spread. Let us look at its implications in the frequency domain. So, let us look at delay spread in the frequency domain, and that will lead us to an important idea known as the coherence bandwidth. Let us consider a channel delay profile h of tau, which is given. So, let us consider a channel delay profile okay, all right. This is a channel delay profile. Now, what I want to do is I will compute the Fourier transform and look at the spectrum of this delay profile. So, let me compute the spectrum of this, which is given as h of f equals 0 to infinity h of tau e power minus j 2 pi f tau d tau. All right. So, I am looking at the Fourier transform of this delay profile, which is h of tau or delay or this impulse response of the channel. All right. Now, let me plot that Fourier transform. Let us say it approximately looks like this. All right. So, it is approximately constant for some bandwidth around 0, then it starts following. All right. It has some kind of a low pass characteristic. All right. So, it is flat. So, let us say this is the 0 frequency component. It is flat for some width around 0, and this it starts falling. Now, this portion or this bandwidth for which the frequency response. So, this is I am plotting magnitude of h of f. Now, this response or this portion over which the response is approximately flat is known as the coherence bandwidth. Of the channel, and this is denoted by the symbol BC. Okay. So, what have we done so far? We have taken a channel that is given as a function of the delay. We have computed the Fourier transform of the channel delay profile. We said that it looks approximately like this, that it has a low pass characteristic. It is constant over some frequency bandwidth, and then it starts falling. All right. And this portion of the spectrum over which the response is approximately constant is known as the coherence bandwidth. You might also have seen low pass characteristics like this earlier, and you might have characterized this as things like the 3 dB bandwidth, null to null bandwidth, and so on, which is essentially that region over which its it has an approximately flat response. It is simply saying that region over which it allows signals to pass. So, in this case we are being a bit more restrictive. We are saying it is not only 3 dB, but it has to be approximately flat, and this bandwidth over which the response is flat of the response of the channel is flat is known as the coherence bandwidth of the channel. This is an important idea in wireless communication. Let me illustrate to you the relevance of the coherence bandwidth. We also know that if I transmit a signal through a system which has frequency. Let us say I transmit a signal with spectrum x of f through a system which has a frequency response h of f, then the output response is simply x of f times h of f. That is, I am taking a signal x of f, passing it through a filter whose response is h of f, the output has a frequency response x of f times h of f. Now, let me take an example. In our system, this is the wireless channel, this h of f is the wireless channel, x of f is the transmitted and x of f h of f is nothing but the received signal, received spectrum or the received spectrum, that is the spectrum of the received signal. Let me write this as this is the spectrum of the received signal. Now, let us look at this in the context of our coherence bandwidth. Let us say I have a wireless channel which looks as follows. This is my channel, all right. This is its coherence bandwidth. This is the bandwidth over which the frequency response is constant. I have a signal whose spectrum looks like this. Let me draw the spectrum of the signal. The signal has some spectrum, all right, but the important thing to note here is that the spectrum of the signal is less than the coherence bandwidth, all right. So, this is the coherence bandwidth, the signal spectrum is limited. Let me call this the bandwidth of the signal. Bs is limited to the coherence bandwidth, that is the maximum frequency component less present in the signal is less than Bc over 2. So, the signal spectrum is limited to the coherence bandwidth. Now, at the output, when I look at the output of this system, since this spectrum is limited to the coherence bandwidth over which the response is flat, I am multiplying some constant with this spectrum, hence at the output my spectrum will be undistorted. All right, look at this. I am saying my signal, this is my h of f which is my wireless channel, this is my x of f which is my transmitted signal, this is my received signal h of f times x of f. I am saying x of f has a bandwidth that is less than the coherence bandwidth, hence if I multiply h of f by x of f, it is simply getting multiplied by this constant which is the flat part or the gain of the wireless channel in the coherence bandwidth, and hence the output spectrum, the shape of the output spectrum is same as the shape of the input spectrum, hence there is no distortion. In other words, there is no distortion. So, what am I saying? Let me write this again. If signal bandwidth Bs, which is the signal bandwidth, less than or equal to Bc, which is the coherence bandwidth, then there is no distortion, in the received signal. All right, because the signal bandwidth is less than the coherence bandwidth, there is no distortion in the received signal, because the signal spectrum is just getting multiplied by the constant part or the flat part of the bandwidth. Hence, there is no distortion. Whatever you transmit is a scaled, the received signal is simply a scaled version of the transmitted signal. However, now consider the slightly different case where I have some channel that looks like this, where this is its coherence bandwidth. So, this is my spectrum h of f, and I have a signal whose bandwidth is much greater than the coherence bandwidth. This is my transmitted signal, its bandwidth. So, this is the coherence bandwidth of the channel, which is the flat part over which the response is constant. I have a signal, but my signal bandwidth B of S is much larger than the coherence bandwidth B C. Now, when I get the received signal, which is h of f times x of f, what happens is this signal is multiplied by this spectrum. In this part, it is the flat part, that is not a problem. However, here it is significantly attenuated. Look at this, here the response is significantly different from the response in BC. So, this part of the signal or this edges of the signal will be attenuated. Hence, what I get, which is this will look something like this, which means these parts, these portions, these are attenuated. Why? Because this signal has a bandwidth B signal which is greater than the coherence bandwidth. So, I am taking my signal, multiplying with the response of the channel. In this part it is fine, in the central part which is less than the coherence bandwidth, it is multiplying, getting multiplied by the flat, but outside the coherence bandwidth there is significant attenuation in the channel, which means the edges of this signal are going to get attenuated, which means what I get is a distorted version of the input signal. Hence, if Bs, which is the signal bandwidth, is greater than Bc, which is the coherence bandwidth, then output or received signal, the received signal is distorted. Alright. If my signal bandwidth is greater than the coherence bandwidth, then because outside of the coherence bandwidth the channel is attenuating, my received spectrum is attenuated at the edges, which means my received spectrum is a distorted version of my transmitted spectrum, and hence coherence bandwidth is an extremely important concept. Let me summarize that here. If Bs less than Bc, no distortion, the signal is essentially restricted to the flat part of the channel response. Hence, this is also known as a flat fading channel. Look at this, my spectrum looks like this. This is the coherence bandwidth, and my signal is restricted to this part in which it is the response is flat. Here the response is flat, hence this is known as a flat fading channel. However, if Bs is greater than Bc, that is signal bandwidth is greater than the channel coherence bandwidth, then there is distortion and the distortion is, look at this distortion, this is my channel, this is the coherence bandwidth, and this is my signal with bandwidth larger than the signal. The distortion in the central part depends on the flat part, the distortion in the edges depends on the frequency response of the channel. Hence, this is also known as frequency selective distortion, which is when the bandwidth of the signal is greater than the coherence bandwidth of the channel. This is h of f, this is s, this is x of f, which is the transmitted signal. The bandwidth of x of f is greater than h of f, then the distortion, the received spectrum undergoes a distortion which depends on the frequency, that is, in this frequency it depends on the frequency response of the channel. In every frequency it depends on the frequency response of the channel. Hence, this is also known as frequency selective distortion. Hence, this is an important idea. If the signal bandwidth is less than the coherence bandwidth, then there is no distortion. If this, and this is a flat fading channel, if the signal bandwidth is greater than the coherence bandwidth, then there is distortion, and the distortion is frequency selective. So, it is known as frequency selective distortion. This is an important idea in 3G, 4G wireless communications. Hence, I urge all of you to again to pay close attention to this concept. So, let me summarize it for one last time over here. Bs less than Bc, it is flat fading, and Bs greater than Bc, it is frequency selective distortion. Okay, so, this is an important idea related to the coherence bandwidth and the bandwidth of the signal. Hence, it is an important idea. Hence, please if you please pay close attention to this idea. Now, let us look at the frequency response that can be explicitly computed from the delay profile. We saw that h of t can be represented as a I delta tau minus tau I. Alright. So, I can represent the delay profile as comprising of multiple paths I equals 0 to L minus 1, each path having an attenuation ai and corresponding to a delay, that is tau I. Now, if I compute the spectrum of this multipath delay profile, that is h of f equals integral 0 to infinity h of tau e power minus j 2 pi f tau d tau, that is I am computing the spectrum of this multipath delay channel. This is a multipath delay channel. I am computing the spectrum of this channel. Now, this is integral 0 to infinity h of tau e power minus j 2 pi f tau d tau. This is the standard Fourier transform expression. This is nothing but 0 to infinity. Now, I am going to substitute the multipath delay profile over here, that is I equals 0 to L minus 1 a I delta tau minus tau I e power minus j 2 pi f tau d tau. This can also be represented by reversing, by taking the e power minus 2 pi j 2 pi f tau inside the summation, that is I equals 0 to L minus 1 a I delta tau minus tau I e power minus j 2 pi f tau. And now, you can observe that integral delta tau minus tau I e power minus j 2 pi f tau is nothing but e power minus j 2 pi f tau I, because integral f of t delta t minus t naught is nothing but f of t naught, alright. So, this is nothing but e power minus j 2 pi f tau I. So, I can write this simply as this Fourier transform as a I e power minus j 2 pi f tau I. This is the Fourier transform of the multipath channel, alright. So, this is the f t of the multipath 3G 4G wireless channel of the multipath this is the Fourier transform of the multipath wireless channel, where I have sigma summation a I e power minus j 2 pi f tau I. A I is the attenuation of the ith path, tau I is the delay of the ith path, and summation I equals 0 to L minus 1 over the L paths. This is the spectrum. Now, let me look at a typical path. Let me look at a I e power minus j 2 pi f tau I. Let me look at a typical path at f equals 0. This is a I e power minus j 2 pi 0 times tau I, which is nothing but e power 0, which is 1. Hence, this is simply a I. At f equals 1 over 4 tau I, this value is a I e power minus j 2 pi 1 over 4 tau I times tau I equals a I e power minus j pi over 2, which is nothing but minus j over a I, alright. Now, look at these two quantities. At f equals 0, this is a I. At f equals 1 over 4 tau, it is minus g I. If a I is real, at 1 over 4 tau I, it has changed to an imaginary number, which is j times a I. So, which means from if f goes from 0 to 1 over 4 tau I, it is changing completely, right. As f goes from 0 to 1 over 4 tau I, the frequency response is changing from a I to minus j I. This is a real number, this is an imaginary number. So, essentially what I am trying to say is, if you plot the frequency response of the complete channel, as we said earlier, it looks like this. It is constant for some duration and then it changes at some point. At some point it starts decaying. What is the point at which it starts decaying? In other words, what is the point at which this response here is significantly different from 0? We can say that point, let me call this point of significant change. Look at this, here the response is a I, here the response can be approximately has changed dramatically. So, it is we are saying this is something like j a I. So, at this point the response has changed drastically compared to what the response is at 0. The point of significant change is nothing but 1 over 4 t tau I. This is approximately what we are saying is, as you start moving from 0 frequency, start increasing the deviation at approximately 1 over 4 t I, the frequency response starts to change drastically compared to what it is at 0. Hence, if you look at it, that this is for the ith path, however, this is for the ith path. Hence, if you look at it on all the paths on average, that can be said as approximately 1 over 4 sigma tau. This is the frequency where the frequency response is significantly different compared to the frequency response here at 0. this can also be termed as, can be termed as the frequency of significant change. Now, you can see, you can also say before this point of significant change, the frequency response is approximately flat and it starts falling after this point of significant change. Hence, the coherence bandwidth is nothing but twice this frequency of significant change, which is twice 1 over 4 sigma tau, which is essentially 1 over 2 sigma tau, where sigma tau is the RMS delay spread. Look at this, let me just repeat this argument again closely. Remember, this is only an approximate argument, it is not an exact argument. I am saying let us look at the frequency response. The frequency response contains components which are a I e power minus j 2 pi f tau I. At f equals 0, this is a I. At f equals 1 over 4 tau I, this is j a I or minus j a I. So, it has changed significantly from f equals 0 to f equals 1 over 4 tau I. Hence, the point of significant change of this spectrum is approximately 1 over 4 tau I for the ith component. If I look at the channel on an average, the point of significant change, because look at this, tau I is nothing but the delay of the ith component. So, the point of significant change can also be said to be 1 over 4 sigma tau on an average, where tau sigma tau is the RMS delay spread, and hence I can say the coherence bandwidth is twice this point of significant change. The coherence bandwidth is essentially this side plus this side put together, it is twice 1 over 4 sigma tau or 1 over 2 sigma tau. Hence, I can write coherence, remember these are all only approximate relations, hence I can write coherence bandwidth as approximately equals to 1 over 2 sigma tau. Right. So, let me again summarize this relationship here. B c equals 1 over 2 sigma tau, where B c, remember B c, this is the relation for coherence bandwidth, B c equals the coherence bandwidth of the system, sigma tau equals the RMS delay spread. And even though this is an approximate relation, this has been found to be true in practice in 3G, 4G wireless communication scenarios and also 2G wireless communication scenarios for a great degree of accuracy, and this can be used as a rule of thumb. We can also look at this intuitively. What this says is essentially that BC, the coherence bandwidth, is inversely proportional to the delay spread. Let us look at this. In a traditional wired communication channel, we have only a single path, that is an impulse. Hence, if I look at this frequency response, let me look at a wireless communication system. This is time, this is frequency. In time, the wired communication system is an impulse, that is its delay spread is 0, its coherence bandwidth is infinity, because the frequency response of an impulse is nothing but a frequency flat spectrum, implies its coherence bandwidth is infinity. Now, as the delay spread starts to increase, that is it starts to spread in time, what happens in frequency? In frequency it starts to shrink, right, because as the time response starts to get wide, and remember for the ideal case where the time is an impulse, frequency it is flat, it is infinity, or the coherence bandwidth is infinity. As the time response starts to shrink, the frequency, as the time response starts to expand, the frequency response starts to shrink. That will be something like this. So, as the time response increases, the coherence bandwidth decreases. In the limit, when the time is flat, that is when the time spread is infinity, when I have sigma tau equals infinity, that is it has an infinite spread in time. In frequency it is simply an impulse, which means B c equals 0. Hence, look at this, the delay spread and the coherence bandwidth are inversely proportional to each other. In time, when I have a single impulse, that is 0 time spread, then my frequency spread is infinity. In the limit, when I have infinite time spread, that is the RMS delay spread is infinity, I have an impulse in frequency, which means my spread in frequency is 0, which means my coherence bandwidth is 0. So, essentially from these figures what I can see intuitively is B c is inversely proportional to sigma tau. Let me write that down again over here. Clearly, the coherence bandwidth is inversely proportional to the RMS delay, right, which is B c, the coherence bandwidth is inversely proportional to sigma tau, and we said one approximation that we can use is that B c equals 1 over 2 sigma tau, that is the coherence bandwidth is 1 over twice the RMS delay spread. This is the approximation that we can use in our computation. Now, let us look at the last factor in this discussion of coherence bandwidth and delay spread, which is the most important factor, which is how does this all come together? What is the relation between this B c and sigma tau? We have looked at it in the frequency domain. Now, let us look at what that relationship is in the time domain. What is, or in other words, simply relation between B c coherence bandwidth and sigma tau, the RMS delay spread. What are its implications? What are the relation in time domain? What is the relation between these two quantities in the time domain? Now, let me consider a signal, a transmitted wireless signal. Let me say this signal, let me consider a base station, all right. Again, let us go back to the earlier example of a base station and a wireless receiver. Let us say I have a direct path and I have several scatter paths arising out of the buildings. So, this is a direct path, there are several scatter paths. Now, let us say I have a transmitted signal that looks like this. Let us say this is my transmitted signal, this is symbol 0, this is symbol 1, this is symbol 2, this is symbol 3, this is symbol 4. Let us say this is my transmitted signal. Now, at the receiver, I get first the copy of the signal which is from the direct path. So, I get symbol S0, S1, S2, S3, S4, so on. So, this is one of the copies of the signal which is arriving from the direct path. Then I have another copy of the signal which is arriving at a slight delay. Look at this signal, the second signal, which also contains S0, S1, S2, S3, S4. Now, this signal which is corresponds to the scatter path. So, what I am saying? I am saying I have two paths. One is the direct path between the base station and the mobile, that is giving me a signal. Then there is also a signal copy, that is the same signal which is arriving at a slight delay that corresponds to a scatter component. This signal is exactly the same as this signal, except that this copy is slightly delayed from this copy. Alright, there is a slight delay. Let me call this Td, that is the delay. Now, you can also see that this delay is nothing but the delay spread of the channel. So, Td equals sigma tau, which is the delay spread of the channel. Okay, so I am saying I am transmitting a signal at the transmitter, at the base station I am receiving copies, I am receiving one signal, and then I am receiving another copy which is coming from the scatter component, that is from trees and buildings, but it has to travel a larger distance. So, it is arriving at a slight delay. That delay is nothing but the delay spread of the channel. So, now due to lack of time I have to conclude this lecture at this point. We will take up this lecture from the next in the next lecture we will start at this point and continue this discussion further about the relation between the RMS delay spread and the coherence bandwidth. What is the intuitive relation between these two quantities. All right. Thank you very much.